just giving definitions of what I mean by these things, one of the goals today is to derive a really remarkable and surprising correspondence, an alternative representation of these, not so much built out of physical on-shell degrees of freedom as may be intrinsically well-defined, the way we naturally are led to think about these things, but in terms of an auxiliary structure in a space called the Grassmannian of k-planes and n dimensions. And we saw a hint of that last time, but now we'll see it in a very different role. It won't be related to kinematics per se, but it'll just be an auxiliary space in which all of these structures can be defined. And to be clear, I mean this for any massless theory in 4 dimensions. So that's the limitation that I'm going to put on myself for today. But before I get to a formal definition, we can just think about what a picture like this thing means. So this is, from this particle here, this internal line is on shell. And you could think about this as coming from summing Feynman diagrams where you take a residue where you put this particular propagator on shell. So you know that it has something like a delta function saying that P1 plus P2 squared is 0. And we could define it for a massive internal particle as well. But at the moment, we just know that this is something, it's not a Feynman diagram, it's something like a Feynman diagram, and you could think about it as a residue of Feynman diagrams. I have some echoing here that I'm going to try to tamper down a little bit. Okay. Now, the meaning of a picture like this, I'd like to define without reference to summing Feynman diagrams. In particular, because Feynman diagrams depend on all these virtual, unseen degrees of freedom, like these polarization tensors and these redundancies that we'd like to get rid of. And there's a pretty simple intrinsic way of defining a picture, or what you mean by a function like this, that follows directly from the principles of locality and unitarity in quantum mechanics. See, locality dictates that if this particle I is on shell, it's a physical state, it could be seen by an experimentalist, it could travel arbitrary distances in space and time, and therefore, in any local quantum field theory, this process on the left and the process on the right have to be independent, and so you should multiply them. And in any unitary quantum field theory, we should sum over a complete set of states. And summing over a complete set of states for the particle I means summing over its quantum numbers and also integrating over its phase space, all of its on-shell phase space, because you're not observing this degree of freedom. So the meaning of this is really just A left times A right, and we can say A left, that's a function of P1, P2, and I times A right is a function of I, 3, and 4. And we're going to integrate over the on-shell, the Lorentz invariant phase space. And there's another way of writing that here, which is in terms of the lambdas and lambda tildes, we can say it's the 4-dimensional integral over the particle i's lambda and lambda tilde modulo GL1 for the modulo little group. So this is a 3-form. There it's the 3-dimensional Lorentz invariant phase space for this particle. And we should also put in a sum over states, but for reasons, well, I'll come back to that in a little bit. I'm going to prefer in this lecture not to put in a sum over states here. Okay. Now, we talked about before that given this helicity assignment of the shaded vertex and the helicity assignments for the empty vertex, that I has to have specific helicity configuration here. In particular, it has to have a plus helicity on this side and it has to have a minus helicity on that side, so that this adds up to h equals 1 and this adds up to h equals minus 1 and this is h plus 1. And if we're talking about Yang-Mills or gravity or super Yang-Mills or supergravity, any theory where we have a single state, a certain representation and maybe some super multiplets generated from it, but where you basically have a single state and CP conjugate, whenever you have that, then it's really a little silly for us to be writing plus sigma, sigma, sigmas everywhere. And so because we only really care about one particular state, and the easiest way of doing that is to decorate this diagram with arrows and to denote the helicity flow through the graph. And so instead of decorating all these pluses and minuses everywhere, I can put an incoming arrow for every minus helicity particle and an outgoing arrow for every plus helicity particle. And for this internal line, we already saw that it has to be like that. And we'll see that the rule here if we're going to talk about, say, Yang-Mills, or gravity, or whatever, that a shaded vertex has all incoming except for one, so 2 incoming and 1 outgoing, and so it's 2 sources and 1 sink, and an empty vertex is 1 source and 2 sinks, depending on these felicities. So this is kind of the general thing, and we can, sure enough, write this thing down. So first of all, this is the full S matrix of 3 particles on the left times the full S matrix of 3 particles on the right. So how many delta functions are there? There's momentum conservation here, that's 4, and there's momentum conservation here, that's 4. So we have 8 delta functions altogether. And of course, among those 8 is momentum conservation across the whole graph. So there's 4 left over, and there are 3 integrals to do. This is a 3 form. I could write D3 lips for Lorentz invariant phase space, but anyway, it's a 3-dimensional integral. So we have 4 extra delta functions, and we have 3 integrations. We're left over with a delta function, and sure enough, that's the delta function. So this thing, whatever it's going to be, is going to be proportional to this, and then delta 2 times 2, lambda dot lambda tilde. So it's got 5. We started off with 8 delta functions. We have 3 integrals. We have 5 left over. And this is what the 5 are going to look like. And now we want to talk about the functional form here. And the functional form is pretty easy to work out from the last lecture, if you were paying attention. So let's go ahead and this integral is also pretty trivial, right? This integral just says that when conserving momentum across the graph, it just says that I is equal to, the momentum of particle I is equal to P1 plus P2, or minus P3 plus P4. Okay. So what we have here, and I'm going to just put spin equal to 1. If you'd like to go back to the general integer spin case, we can just raise it all to a power s, or sigma. But so the left amplitude from last lecture, we have it's 2, 3 cubed in the numerator, divided by I1, and then 2I. That's what we have. And then on the right-hand side, we have the square bracket version of this, which is 3, 4 cubed. And then similarly, we can walk around the graph and see it's I 3 and 4I. Now, momentum conservation, so tells us that Pi is equal to P1 plus P2, which is equal to minus P3 plus P4. And in terms of spinors, we can write this as 1 angle bracket square bracket 1 plus 2 angle bracket square bracket 2. This is good if this is fun to play with if you like playing with notation. What? Yes, it's 1, 2. Very good. Thank you. In addition to the normal mistakes, I will actually be putting in a few on purpose to catch you, to see if you're paying attention. Okay. So we can actually just do this algebra here. So we look at this factor here. And so we're looking at what Pi is, and we're thinking this is Pi, which we can think of as I angle bracket I square bracket, which is the lambda and lambda tilde. And if we insert this expression inside here, well, what do we get? We have 2 terms. This product here is going to turn into 2 terms, but the first one is going to give us 2, 1, and then 1, 3. Okay? And then the second term is going to give us 2, 2 plus angle bracket 2, 2, 2, 3. But this is a determinant of a matrix whose columns are lambda 2, lambda 2. This is antisymmetric, this is 0. So we just get this. And similarly, we can do the 1 and 4 case, and I'm going to use the other solution here, and it becomes, and I'm going to put a minus sign. I'm actually being careful about this, that we get 1, 3, 3, 4. I'll leave that. You can do the next step yourself. And so what happens when we put all this together? So if you can read this, we have so we have angle bracket 1, 2, that's going to cancel this. Square bracket 3, 4, that's going to cancel one factor from that. And then we have this angle bracket, square bracket. And I'm going to erase this denominator. This is what we get. So after all the dust settles here, we have angle bracket 1, 3, square bracket 1, 3. There's another name for that. This thing here is also known as P1 plus P3 squared, which is often called U. So we can write this as over U. So this is the kinematic prefactor which goes inside there. And we got it just by multiplying everything together, and we solved all the momentum conservation constraints, and we just followed our nose. And that provides us with a definition of what this is that, importantly, from a philosophical or moral point of view, didn't come from starting from Feynman diagrams. We gave a definition of what this thing was intrinsically. And this generalizes to an arbitrary graph built out of on-shell scattering amplitudes. And they don't necessarily need to be trivalent, but actually, for the purposes of some of the formulas I'm going to write, let's just assume they're all built out of these little trivalent graphs everywhere, just so that I don't have to qualify things later. So let's suppose that we have a graph built out of these little trivalent vertices. So an on-shell function, and again, I apologize for this the name on-shell function. It's just not off-shell. For any graph whose all the edges are these internal propagators or particles being propagating, and the vertices are scattering amplitudes, is going to be the integral over the on-shell phase space over each of the internal particles. So for every internal particle, we have d squared lambda I, d squared lambda tilde I, mod GL1, so this little 3 form, and then the product of all the amplitudes at every vertex. So there's a similar definition that is very close to this, and depending on exactly the details, it's either identical to this or it's very close to this, would be the residue of you take all the sums of Feynman diagrams and you compute the residue on the cut. That may or may not differ by a Jacobian. But anyway, this is the definition I want to work with here. So it's a product of this integrated over the on-shell phase space of every particle. And I would ordinarily put in a sum over helicities or other quantum numbers for the all the internal lines, but I'm not going to here, in part because I'm going to decorate all my graphs with that information, which means I don't want you to sum over the ones on the inside. So examples of other on-shell diagrams. So this is a pretty trivial on-shell diagram. It's probably the most important one, or the kind of the baby diagram. Okay. So I just want to draw a few more. And I also want to be clear that actually, although I'm talking about massless fields in 4 dimensions, this definition has absolutely nothing to do with 4 dimensions. I mean, this notation does. But if I wrote d minus 1 Lorentz invariant phase space, this would be a valid definition for what you meant by these kinds of pictures in a general quantum field theory in general numbers of dimensions. It's a meaningful gauge invariant thing because all the building blocks are gauge invariant. But we can start gluing them together in a more interesting way and get a more interesting variety of functions. So for example, and now I'm going to use this notation where everything I'm drawing here is, say, n equals 0, just pure Yang-Mills, just for the sake of convenience, but I'm going to use these arrows here. So suppose we have 1, 2, 3, 4, and let's say it's minus helicity, plus helicity, minus helicity, and plus helicity. So remember, outgoing is plus and incoming is minus. And then I'm going to instead of summing over all the helicities that could flow inside this graph, I'm just going to write this one. And I'm going to leave it as a small exercise to see. You can do this at home tonight. It's nice that this is equal to angle bracket 1, 2, 3, 4 over 1, 3, 2, 4 cubed times a tree with minus, plus, minus, plus, where a tree includes as the Park-Taylor factor, where we put the where we have 1 3 to the 4th power in the numerator, with its delta function and everything. Notice that this is not the tree amplitude. You might have heard that boxes are trees. This is an interesting thing to, anyway, it's not true here. And it's also not equal to the diagram with the arrow, the interior arrows reversed. That's a different answer. It's also proportional to the tree, but it's not this factor. Okay, but we can draw pretty complicated diagrams. So let me just draw one more in pure Yang-Mills that's scary enough to be maybe considered general, although I should probably add more external states. But this is a pretty interesting counterexample to things. Okay, so I'm just, bear with me for a moment. So it's actually, this is an all plus thing. All the helicities are flowing outwards here. So it's 1 plus, 2 plus, 3 plus, 4 plus, and it's non-planar. And the arrows here go in, out, in, out, in, out, out, and like this. And I will leave you to confirm that this is a, that all the arrows are such that every white vertex, like this white vertex, has 1 incoming and 2 outgoing, and every shaded vertex has 2 incoming and 1 outgoing. And sure enough, if you put this, and I encourage you to do this, please, I'm not going to write down the answer here, but you can put this on in Mathematica, solve for all these on-shell conditions. So you just draw some arbitrary graph here, you put everything on shell, you conserve momentum at every vertex, and you choose the solution where the lambdas and lambda tildes are aligned this way, and you will get something that is non-zero, and it's an interesting function. Okay? This is for generic external momenta. And we can keep going with this. Before we get too far in that direction, we're going to have a, well, let's just first talk about some of the general characteristics about these diagrams. So general descriptions. Describing diagrams. Okay, so there's some, you have a general graph, there are some, this is really just laying down some notation here. So first bit of notation, n is trivial. N is the number of external legs. Okay, and for these trivalent graphs, this is 3 times the number of vertices minus 2 times the number of internal edges. Okay, there's another very important characteristic for all of these graphs, which is k, and it's, in terms of, in Yang-Mills pictures, it's a negative number of minus helicity gluons. But more generally, what I really mean is that it's the number of sources, if you decorate the graph in this way. By the way, a graph which has 2 colors, all trivalent vertices, where all the shaded vertices have 2 incoming and all the white vertices have 1 incoming, is called a graph with perfect orientation. So k is the number of sources once you give the graph a perfect orientation. And this is 2 times the number of shaded, and I'm calling it B for black, and I apologize, this is a whiteboard, okay, but you get my picture, and the number of white, which again is empty. So this is shaded, number shaded, this is number empty, minus the 1 for each internal line. Another important characteristic is the number of net either integrations to do or delta functions. And I oscillate personally between which one I like thinking about more. So let's just say number of delta functions. Or let's say number of, let's say net integrations. So this d hat, and there's a hat because I'm going to define some other d later, is the number of net internal degrees of freedom. Okay, and for these kinds of pictures here, every picture here we're talking about is in 4 dimensions now, so I'm going to erase this d-dimensional stuff. We're going back to 4D. So how many degrees of freedom? We have 3 degrees of freedom for each internal edge, and we have 4 delta functions per vertex. However, of the 4 delta functions per vertex, one of the delta functions always, any graph of momentum conserving vertices will conserve momentum across the graph. So you can always pull out an overall momentum conservation. So the net number of internal degrees of freedom, which is how many things you have left after you've integrated out as much as you possibly can, if you can, is this number. Okay, so for example, let's just look at these graphs on the board here. So what is n for n? This is, well, these are all 4 particle things. So n is 4 for all these pictures. K, can somebody tell me what k is for this? Number of sources. 2. Here, 2. Here, 0. K equals 0 for this one. D hat. Somebody shout it out. It's, the number of net internal degrees of freedom. If you follow that formula, it's -1, okay? Which is another way of saying that you have a net 1 constraint on the external data. So it's net delta function. So there's a related thing here for this. I could say it's delta hat, which is the number of constraints. And again, these numbers, this language really assumes that you can soak up every delta function with every integral. That's not always true, but anyway, the combinatorial definitions are a little more robust. So it's minus delta hat, or d hat. Okay, so if d hat is 0, okay, so what is this d hat? Anyone tell me what? So here, let's just do it the slow way. So how many integrals do we have to do? We have 3 times, there are 4 internal edges, so we have 12 integrals to do. 3 phase space integrals per edge, 12 integrals. How many delta functions do we have? We have 4 at each vertex, so we have 16 delta functions overall. That's 4 across the graph momentum conservation, and 12 left over. So you have 12 delta functions, 12 integrals, everything's locked. That's why you just got this rational function. And in general, if you sum over solutions, it becomes rational, but more generally, these are algebraic things. So if d hat is 0, it means that you're talking about some algebraic function that is generically non-vanishing, usually, most of the time, for generic external kinematics. And if d hat is positive, so in this case, d hat, has anybody gone ahead of me? Tell me what d hat is for this. How many internal degrees of freedom you have? Well, if you put this on the computer, you'll figure it out that there are 4, there's a 4-dimensional family of solutions to all these, once you've done all the integrals, once you've locked all the delta, you've soaked up all the delta functions. So this has d hat equal 4. And it's kind of interesting. So these pictures where we draw edges and whatever, they span a whole variety of useful objects in quantum field theory. They include things that are distributions on external kinematics. This is generically non-zero because there's a delta function. It only has support when, and I wrote p1 plus p2 squared, but I could actually say, be more specific and say delta square bracket 1, 2. So it has distributional things are included in this vocabulary, and also integrals over here. And we'll see that some of these things, and at least in certain quantum field theories, the loop integrand can be directly expressed in terms of integrals with d hats greater than 0. So the change of variables is kind of interesting and non-trivial, but that there is a strict sense in which these integrals over these on-shell degrees of freedom can be exactly matched to the d4Ls in 4 dimensions at least. So there'll be some more characteristics here. But before I get going to, let me just say, so okay, I'll write this thing out and we'll fill out the details later. So I'm not going to show this in the generality that I'd like to, mostly just because it involves carrying around extra notation. So, but I will do it in one particular case, which is for maximum supersymmetry, which I will get to in a moment. But what we're going to see in the second half of this lecture today is that on general grounds for massless theories in 4 dimensions, all of these on-shell functions, any graph like this, can be represented in the following way. As some volume form here, so this is just some auxiliary space I'm calling C, with the following system of constraints. So k by 2 c dot lambda tilde, and sorry, well, maybe I'll leave it to the people paying close attention. Okay, I won't correct myself. Lambda dot c perp, where this is a some volume form that in general depends a lot on the graph. It depends both on how it's decorated, how the arrows are distributed. If you have a theory with more than one kind of particle, so not just a gluon and an anti-gluon, not just 2 helicities of one state, but if you had to talk about the standard model, then these on-shell diagrams would carry a lot more information. You'd have to tell me what on each of these internal edges, what particles are propagating there. So, and in general, this volume form will depend on all the vertices. We're going to construct this correspondence explicitly. So it's some volume form on the Grassmannian of k planes in n dimensions. And C here is a subspace of the Grassmannian of k planes in n dimensions, where k and n are as above. So the number of sources there. Okay, and this really follows in general by just knowing what these 3 particle vertices are and gluing them together in a procedure that we'll get to at the end of this lecture. So, but in certain quantum field theories, these volume forms are very nice. So for example, well, we'll get back to that in a little bit here. So this is just, so C here is just some auxiliary space. It's not the on-shell degrees of freedom, although it's kind of parameterizing it. But it's a nice place where you can now understand relations among on-shell functions, can be understood like functional relations, can be understood as geometric relations inside this space. Homological identities here. Also, diffeomorphisms that preserve the volume. If you have a volume-preserving diffeomorphism here, that can be recast through these delta functions as active transformations on lambdas and lambda tildes. And if you preserve the volume, then this integral here will be invariant. And so volume-preserving diffeomorphisms are symmetries of these on-shell functions. And in particular, in the case of planar n equals 4, if you ask for what are the volume-preserving diffeomorphisms that preserve all graphs, turns out that's the Yangian. So it's an interesting kind of interpretation where you don't bake that in. But on general grounds, provided the space of volume-preserving diffeomorphisms it's typically infinite dimensional, and if it is infinite dimensional, these pictures usually enjoy infinite dimensional symmetries. There are a lot more things to be said about this, and I'll come back to it as we go on. But at the moment, I want to stop drawing all the arrows. And so I want to take a side, pause, and step back, and introduce some notation about what should be everybody's favorite quantum field theory in 4D. If it's not your favorite quantum field theory, I can just start by apologizing. What I'm describing right now, especially insofar as these lectures are talking about tree amplitudes, there's no difference between the gluonic components of maximally supersymmetric or non-maximally supersymmetric. Supersymmetric Yang-Mills, the gluonic part of it and the gluonic part of pure Yang-Mills are exactly the same at tree level. And the reason is because you can't draw any Feynman diagrams. You won't create anything but gluons on the inside of the graphs. So you know that at least at tree level, all the supersymmetry is doing is bookkeeping. And it's actually incredibly powerful bookkeeping. It's very valuable. So I hope that you'll bear with me with a little bit of notational heavy-handedness here to talk about a particularly nice quantum field theory. Oh, I should say, why is it maximum supersymmetry and why is supersymmetry playing any role at all? The reason is because, as I was talking about, even if I have a theory with a single state that I care about, like a gluon There are two helicities to talk about in any massless quantum field theory in 4D. I have to care about the CP conjugates. And that means that in terms of these diagrams, I have to draw arrows everywhere. And the answer depends on how the arrows are drawn. I'll leave that as an exercise, but this particular picture, if you change the arrows on the inside, you get a different answer. And that's just annoying. So to save myself some time, I would like to use a theory where the plus helicity state and the minus helicity state are related to each other. And that's what happens in maximal supersymmetry. Not less than maximal, but only in maximal. So it's an interesting thing about this on-shell diagram universe that like a little bit of supersymmetry buys you nothing. It's like totally unhelpful. But maximum supersymmetry buys you a lot because suddenly you don't need to distinguish between plus and minus helicities. So let's talk about the simplest QFT, which is n equals 4 maximal super Yang-Mills in 4D. Okay. Now, those of you who know a lot about supersymmetry or are experts on supersymmetry, this is going to be kind of elementary and kind of trivial, because the only thing that I care about for this on-shell diagrams and whatever is the on-shell part of supersymmetry. And on-shell supersymmetry is like chapter 1 of Wesson-Bagger. That's the trivial part. All the hard stuff is when you start talking about Lagrangians and preserving, super transformations. The on-shell part of supersymmetry is a pretty easy thing to describe. And I'm trying to see how much detail do I want to go into here. I'm going to cheat a little bit and avoid some notation, but I put a reference where you'll find the extra indices and things in there, 0808.1446, which this is one of the answers to the question raised in that title. So the idea here is that if you have n supercharges, you have these supercharges Q and Q tilde, and well, let's see, how far do I want to go here? Alpha dot A for the 8th particle, and it takes a state of some particular helicity A, and it maps it to lambda tilde alpha dot A, and it lowers the Q bars I'll have as lowering operators, so HA minus a half. So this is kind of the standard thing, but we can decorate this with, sorry, not QA, what am I saying? Well, yeah, that's fine. If you have n supercharges, there's an extra index here, and I runs from 1 up to n. Right. Maybe I'm going to skip over some of this extra notation to here. And let's just talk about what we're going to land on, which is diagonalizing our external states, our Hilbert space, with respect to supersymmetry generators. So let me just cut to the chase and tell you what I'm going to talk about. So the punchline of this is that to describe a supersymmetric theory, we want to define what are called Grassmann coherent states. And roughly speaking, they are these Q tilde I. You introduce some extra variables eta tilde for each particle A. And now the Q tildes, because they lower the charge, they will annihilate the minus helicity gluon. So we start at the top helicity state, the plus helicity state. I'll put the plus on the outside. Consistent. So you just put in this exponential, just like you would like e to the IPX. This is like the supersymmetric generalization of that. What you get is, so you have a plus helicity state. You also have eta tilde, I'll put the i's up here, A. And now you have, for plus 1/2 helicity, you have I of them. Then you have 1 over 2 factorial, eta tilde I A, eta tilde J, 0, ij, plus, and I'm only skipping over one term, but still, 1 over 4 factorial. I almost can't bear to write this whole thing out, but I will. J, K, L. The minus helicity state, the minus 1. So this starts off at a plus helicity gluon. goes down to a minus solidity gluon ijkl. Because these things are anti-commuting, I'm going to rewrite, I can think about this instead as including the 1 over 4 factorial, I can write it as eta tilde 1, the one component, eta tilde 4 A. And later I will find it useful to write a kind of deceptively compact notation and say that is eta tilde of the 8th particle to the 4th power, which it is absolutely not any eta component to the 4th power. Those anti-commute, that doesn't happen. This is all 4 charges, okay? I equals 1 all the way up to I equals 4 for n equals 4. So that's what I will think about here, like that. Okay. Now, so a function of these superstates, instead of describing the external states in terms of the momentum and the helicities, we're now going to be talking about what I'm going to call superfunctions, which are functions of lambdas, lambda tildes, and these eta tildes. And in order to extract a particular component out of this, you can do a fermionic integral. So you integrate out the etas to pick up a particular component here. But every on-shell diagram, and we'll see that it kind of follows from that, but it'll be useful for you to think about supersymmetry in a very compact way here, which is not true for all superfunctions. You can write down lots of superfunctions that can't be written this way, but everything that you'll see in these lectures can be written this way. And maybe I'll keep the n just for the sake of generality. K times n, C of lambda, lambda tilde. This does not necessarily have anything to do with that Grassmannian, but you'll see that it does. Eta tilde. Okay. So what I mean by that is that these on-shell diagrams we're going to draw, or amplitudes, or whatever else, are functions of bosonic data, lambdas, lambda tildes, and a fermionic bit of data. But this fermionic bit of data is organized in an extremely simple way. In fact, it's organized as it's a bosonic function, f, that just depends on lambda and lambda tilde, times this fermionic delta function. Now, I hope all of you learned in quantum field theory class how fermionic integration works, but I'm not going to review it here, but just suffice it to say this is the same as the product of all the components, because integration integration is trivial for these things. So integral delta is the same as integral for a fermionic argument. So this thing is some k by n matrix. C is some bosonic k by n matrix. And in particular, when we get to Mathematica on Friday, I'm going to associate these superfunctions with a pair of bosonic data, f of lambda, lambda tilde, so a purely bosonic function, f, combined with this matrix C. So at no point do I need to teach Mathematica what a fermion is or how it anti-commutes. All I need to do is I need to encode this function, and that function is encoded by this thing and a matrix of functions. So let me define what this delta function is here. So delta k by n, by cal n, c dot eta tilde, you can just take it to be defined as the follows. This is the output of taking into account all the anti-symmetrization here. It's the product from I equals 1 to n, cal n, so 1 to 4, of the sum of all ordered lists, k-tuple lists, A1 up to AK, of det, the minor of this matrix built out of the columns CA1, CA2, dot, 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 CAK. So a k by k minor of this k by n matrix, so C is some k by n matrix, and it has columns C1 up to Cn, just like we did for our lambdas. So it's a determinant of this particular minor of this matrix times eta tilde I A1, eta tilde I AK. So you can think about this fermionic delta function as being just a vector of a ton of particular components. And I'll show you an example of this in a more illustrative example in a moment. But but what you can view is that this is just, you pick n choose k minors of this matrix, and you pick 4 of them, or n of them, if you have n supersymmetries. So that's what every component function is. It's just a choice. So out of this particular bosonic data, you extract components. Like if you want to look at the gluonic part of n equals 4, all you do is you just pick out a particular k by k minor of that matrix, and you pick it out 4 times, so you pick up all the etas of each of those particles. Okay? All right, let's see what this looks like, this fancy notation and some examples here, which are the 3-particle S matrices. So from last time, we had this, oh yeah, and because the plus helicity and the minus helicity are related by supersymmetry, we don't need to distinguish anymore their helicities. So there's really just a superfunction depending on, there's one superfunction of this type, and then there's another one of this type. And yes, my definition of K matches the previous definition of K. So I'm going to leave off the FABC. I'm just going to write the kinematic parts from here on out. 1, 2, 2, 3, 3, 1, times an instance of this fermionic delta function. This is a 2 by 4 fermionic delta function of lambda dot eta tilde. So in this case, C is equal to the matrix lambda, okay? Times delta 2 by 2 lambda dot lambda tilde. Okay? And for the empty vertex, it's not exactly the same, and it's not the same as just switching all the angles, all the angles to squares. And the reason, I hope if you've been paying attention, is that I really broke some symmetry between pluses and minuses. Because I defined my coherent states to lead with the plus, and I'm using these eta tildes, it's a very asymmetric presentation. This is balanced towards the pluses. Minuses cost you etas, pluses cost you nothing. So there's quite a distinction between these two. In this formalism, you can have another formalism where that's not the case. But, so this is a 1 by 4, where the matrix in this case is lambda tilde perp dot eta tilde. Okay, I'll remind you what that is in a second. 2 by 2 lambda dot lambda tilde. So just to remind you that lambda tilde perp is the matrix whose first, it's a 1 by 3 matrix whose first entry is 2, 3, and then its second entry is 3, 1, and its third entry is 1, 2. Okay, so it's this particular 1 by 3 matrix. And if we expand out these fermionic delta functions, what we just get is a giant list of bosonic things times particular sets of etas. And those things have meaning. They're called component amplitudes. So for example, when we expand out this delta function, we need to take this, we have this matrix lambda, which is lambda 1, lambda 2, lambda 3, the 1 component, the 2 component. So it's just this little 2 by 3 matrix. And what do we get when we expand out, when we use this definition? We're going to get 3 choose, it's a 2 by 3 matrix. So this is going to give us 3 choose 2 to the 4th power components. Right? Every minor you can take 4 times. And so among the particular things you could take is that you could take the minor involving columns 1 and columns 2, for example. And that'll give you, and you take it 4 times. So that'll give you 1, 2 to the 4th power times eta, and this is where my sloppy notation is going to come in handy, eta 1 to the 4th and eta 2 to the 4th. And this, well, actually I should put, this is inside here. Well, times what? Times 1, 2, 2, 3, 3, 1. And this thing here has another name. It's called the particular component of minus, minus, plus. Okay? Plus lots and lots of other things. So we have 3 to the 4th particular component amplitudes. And this is all organized into a single superfunction. And this is why supersymmetry in this formalism is nice. Instead of, if you talk about Lagrangians or the field content of supersymmetric theory is worse than non-supersymmetry, right? You add more supersymmetry, you add more crap, you add more fields, whatever. In this case, you do add stuff. You have 3 to the 4th power different particular components, but they're all the same thing. They're all just related by different choices of these minors. So for example, if we take another piece here, we would find like eta 1, the 1 component, the 1 component, yeah, let's do that. So we need to pick out, so that would be times minor 1, 2, and we could take eta, they have 4 different minors, so we could take 2, eta 3, the 2 components, eta 1, eta 3, the 3 component, and say eta 2, eta 3, I don't know, I'm just 3, the 4th component. So the coefficient of this particular term in that is angle bracket 1, 2, angle bracket 2, 3, angle bracket 1, 3, angle bracket 2, 3, right? And we're going to divide by this denominator because it's there everywhere. So 1, 2, 2, 3, 3, 1. And that means that this thing turns out to be minus 2, 3, which is also known as the amplitude involving what states? So here we've picked up the eta. For particle 1, we have components 1 and 3, and that means it's a scalar phi with r charges 1 and 3. That's another name for this particular thing. I'm going to call it phi ij. For particle 2, we actually pick up 3 etas, 1, 2, and 4. And that means it's a psi, a minus helicity psi of, so a fermion. We've gone 3 levels down, and it's 1, 2, 4. And then particle 3, it's 2 and 4, so it's another scalar. Scalar 2 and 4. Okay, so it's a scalar-scalar fermion interaction. And there's a lot more terms. You expand it all out to death, and what you can get is if you want this component, you just pick out a particular set of minors of this matrix. And similarly here, so in this line, what do we get? Now it's a 1/4 matrix, and so it looks a little bit simpler. In particular, you just pick out 3 choose 1 to the 4, although of course it's the same number as that. And among its components, for example, would be eta 1, all 4 components of eta 1, which would be, you pick out the 1/1 minor, this particular 1/1 minor. So it's 2, 3 to the 4th power divided by 1, 2, 2, 3, 3, 1. And this is also known as the one where it involves minus, plus, plus. Yes, absolutely right. I should have. Yes, also from the helicity sum. Yeah. Very good. Okay. So this is on-shell supersymmetry. Let me just recap, and then we'll take a 5-minute break in the spirit of things. So if you don't care about if you do care about supersymmetry, this is the right way to think about n equals 4. Every Yangian invariant you will ever write down will look like this. It will be written as a product of some bosonic thing this way. Sums of things don't get factorized like this, so that's the kind of exception. But this is an extremely useful way of packaging and talking about supersymmetry. It will also be very closely related to all this technology we have here. And in fact, this is how the Grassmannian was discovered. And well, halfway, one of the ways it was discovered was just by noticing that when you looked at different component amplitudes out of a given superamplitude, that they were related by the ratios of minors of a matrix. And so you naturally started, you had all the things, all these, the terms in BCFW, all the ways that people were writing amplitudes, had the the feature that when you took ratios of terms, you just got different minors of this matrix. So it caused you to think about this matrix. And it turns out the matrix is this Grassmannian and plays this special role. So if you don't care about supersymmetry at all, this is a fantastic bookkeeping device. One, it means that you don't need to decorate these arrows ever. You can take, especially if we're talking about tree amplitudes, you just take the super thing, and then if you want gluons in slots 1, 3, 5, and 7, you just take minor 1, 3, 5, and 7 to the 4th power, and you just multiply that through on every term. So it's very simple. So to take a particular bosonic component from a superfunction is very easy. And we will see this in practice on Friday when we implement the tree amplitudes in this supersymmetric language in n equals 4. In Mathematica. Okay, so let's take a 5-minute break, and then I'll come back and we'll build up this Grassmannian correspondence.